Hello, and thank you for joining us on our presentation about informing government policy decisions. Our agenda includes a task, pre-processing, data exploration, data modeling, results, and finally, if you have any questions. So, first of all, what is our tasks? Our company tracks social media interactions related to civil unrest. Traditionally, the task was to use this data set that used to be explored manually to identify themes that are political and non-political and create a document classification system that can use the technology and the an artificial intelligence algorithm that is learning to classify data between political and non-political. The result will be to save money by avoiding human labeling and enable quicker identification of users and related text. So, pre-processing. What is the anatomy of a tweet database? We have tweets in our database that are related to political discourse and not related to political discourse. First of all, our data has three columns: document ID, text, and label. Label is whether the tweet is political or not. One, as you can see in the first tweet, is talking about Joe Biden, so it is political. Zero, such as the second tweet, is not political. The text of the tweet appears in the middle column, titled text. How do we pre-process the data? First of all, we import the test data of 2,000 tweets. This appears in a database in a CSV format. We import it in the R Studio, which is our tool that we're using to program with our programming language. We identify the stop words. So we use a library that has about 500 or more commonly used English words, which we need to take out because otherwise these words would cloud the analysis and will render it meaningless. We add custom words. Later on, we will use our top three so that we can see what other words show more often. We build a volatile corpus, which is basically a document collection of data. We clean the data by removing the stop words and other items such as punctuation. We lowercase the data, and we clean it using a function called clean corpus, which we built in the R programming language. Finally, we create a matrix. This matrix is either term document matrix or document term matrix. In a document term matrix that we will use for the algorithm, the documents, the tweets are lines, and then the terms, the tokens, or the words within the tweets are columns. As you can imagine, because words are plenty and the tweets are not all touching on all the words, the data is not dense. It is pretty sparse. It has a lot of zeros. So let's explore the data. We have our top words on the top. Now, the left side has all the top words that are not stop words. You can see that rainbow, zombie, and unicorn that do not seem political appear as top three. So on the right side, we took them out and we can more clearly see that words that appear more than 50 times are words such as CNN or protests, which are seemingly political. On the lower side, we have two other representations. On the left side, it's other items that are not words, such as RT, which indicates retweet, or HTTPS, a hierarchical dendrogram, which might indicate association between words. In this case, they're not clear associations, and it also plots the linkages between words. You can see the linkages more clearly here where we're doing a word association. So for example, rainbow, it appears associated to this K-pop band called Rainbow Hashi, also associated to pride. Now we got zombie associated only to apocalypse. Again, association for us, it has to be more than 0.2 to be meaningful. Ideally more than 0.3. So you can see that for the political words such as CNN, it's related to Atlanta. Maybe something happened in Atlanta during the tweets, and protests are related to George Floyd and police brutality. Next, we will look at a word cloud. In this word cloud, we can see the words in a cloud of words. Now, zombie, rainbow, and unicorn appear the largest. So let's take those out and see what it looks like. Well, we got words such as COVID, CNN, people. We used a different color palette here so that we can see perhaps other interesting highlights. Again, the top three words, we take them out. We got items such as Black Lives Matter appearing quite prominently, CNN, people, Trump, Antifa. So it's very interesting. And we can look at this and try to find words that stand out to us. Let's jump into data modeling. Now, for data modeling, we're using a technique called elastic net regression. That's a mix between two techniques called ridge and lasso, least absolute shrinkage selection operator. So we will take the data, we'll separate it in training data and test data. That's about 1,800 and 200 because we're working with 2,000 tweets. That is our data that we will use for testing. A little bit about ridge and lasso. So ridge is basically trying to do a penalized fit so that while we're training the data, it cannot be fitting it perfectly because once we do the test, this line, if it would be fitted perfectly, it would basically never consider the test elements that are similar. Lasso is basically cutting off terms that it considers meaningless. So it will reduce the words that affect the model. So in our case, we basically put a coefficient of alpha at 0.9. So the coefficient of alpha is basically telling us how much of ridge and how much of lasso are in the elastic net. In our case, we put more on lasso because we wanted to drop a lot of terms so that the model is more stable and solid. So as we will show you later, it worked pretty well in the prediction probabilities, so we're satisfied with our model. So partitioning, we covered it. It's this figure here, the test model. We tested, again, on the validation portion of 200 tweets, and then at the end, we will apply it on the new data set of 1,000 tweets to see how it operates, how it can predict on tweets that the model has never seen before. So again, lambda, minimize sum of squared errors. That's how ridge works. Now, the results. What are the results and how do we interpret these? So as we explained to you about the train data, the 2,000 tweets, we separated in a planning and a test data set. So when we got our train data set, if you wish, when we had stop words, it was basically doing okay. Like this is the probability, 0.89% prediction on the train. But then when we were testing it, it was pretty low. So once we cleaned up the text, it performed pretty well in both. And you can see here the results. So for example, the way you read this is that these are the predictions of the model. So like you got, it was predicting that 1,277 tweets were not political and 349 were political. But in reality, the political tweets were actually the ones that it got right and the ones that got wrong. So it would be the 349 plus the 158. The same with our test data. It predicted 46 were political. In reality, it was about 55 that were political. So a pretty good prediction probability, 90%. Then we applied it to the 1,000 tweets, and we got basically 200 tweets predicted to be political and 800 to be not political. If we look at the data that we exported, it was basically tweets such as this one that's talking about Black Lives Matter that was predicted as political, and this tweet about rainbow, it says it's not political. It looks not political to us, but again, you can take a look at the data and see how the predictions actually did. We don't have a percentage of prediction because we do not know whether these tweets are political or not. We basically had live data, which has never been scored before. So with all that, we thank you very much for watching our presentation. And if you have any questions, please go ahead and we will be happy to answer to you. Thank you very much and have a great day. Goodbye.